All right, we gave a little bit of an introduction into what subsurface modeling is. Don't worry if you feel unsatisfied by that. I will definitely provide a lot more details about how to put workflows together, philosophy, general strategies for subsurface modeling. So we're just getting started. Okay, so let's get into the subsurface data. Let's talk about what data is available to us. If subsurface modeling is a grand data integration challenge, well, what's that data that we have to integrate? Well, there's various sources of information that are available to us in the subsurface. So data may be compared or discussed with regard to three different criteria or descriptors. What's the information? Now, everything comes down to the properties of interest in the subsurface. So we want to know, what does the data tell us about a specific property of interest within the subsurface? Static properties may include reservoir facies or rock types, porosity, permeability, saturations, and so forth. Of course, unconventionals will challenge us to have brittleness, vitrinite reflectance, total organic carbon, and so forth. Dynamic properties, of course, would be more like pressure, flow rates, velocity, compressibility of the rock, and so forth. So that's the information that's available. It's what property of the subsurface that the data is telling us about. Resolution. What's the scale of the measurement? Now, if you extract a core plug from a core and you were to apply a permeability calculation on it, it would tell you about the permeability over a scale or resolution like that. Ideally, if you were to extract many little core plugs, you would have permeability at 2 centimeter resolution. Every 2 centimeters you have a core plug and you would know something about permeability. As opposed to if you were to calculate the permeability over an entire core sample, now your resolution is lower. It's a larger scale over which you're making the measurement. Now, of course, if you have gamma ray, well, the gamma ray measure is maybe penetrating a meter or two into the rock, and although it may report every half foot, it's probably averaging vertically over a larger volume. And so our petrophysicists may tell us that it is recording at a certain resolution, that beyond the averaging, that there's a certain resolution that's available, maybe a foot or two or something like that. Seismic acoustic impedance. Acoustic impedance is really useful. It tells us something about rock properties. It can be somewhat correlated to porosity. And depending on the velocity and the density of the rock and so forth, you might anticipate that the resolution maybe vertically is 10 meters or maybe less. It depends if you're shallow, if you're deep, and so forth, what's the frequencies available to you. So this is resolution. It's getting at the idea that it's just like if you're looking at your screen and you're imagining, you're watching HD and you're imagining the good old days when you didn't have HD and it was much lower resolution, you don't see as much detail. This is exactly what we're talking about, is how small of a subset of the reservoir can you resolve and measure the property of interest. Coverage. Now, coverage is extremely important. Information is often very sparse in the subsurface. So I would define coverage as over what proportion of the subsurface is the measurement typically available. Core samples are somewhat infrequent. They're rare. It's expensive to extract core. Well logs are often available over most vertical wells, and so there'll be much better coverage than you would say get from core. And then of course you have 3D seismic, which might actually have complete coverage of the entire reservoir and even the overburden to the reservoir. And maybe even the underburden. You're able to see quite a bit, of course, at a much reduced resolution. So these are three ways to describe data. Of course, we could have talked more about accuracy and the complexity and whether they're direct or indirect measures. There's so many things we can talk about when it comes to data. But these are three ways to summarize. Now, of course, when we talk about dimensionality, we might not be working with data that's all 3D. We model in 3D, but often our data sources are not 3D. Consider a one-dimensional data recorded as a sequence of distance or time. A well log is recorded in distance. Production is recorded over time. These are all one-dimensional data sets. There are variations in vertical distributions, mineralogy, mechanical properties. They're very useful, they're interesting, and of course we can correlate, in the case of a well log, away from the wells. We can tell something about the framework and so forth, and move away from 1D. So these can be very powerful, but we do work with data that may be sampled one-dimensionally. We may also work with data that's sampled 2D. Geologic maps are a great example of that. We might have two-dimensional representations over the unit of interest, the reservoir of interest, of what was going on as far as the paleo situation, the sources, the locations of major deposition, and so forth. We might be able to see that all and have that available based on interpretations of seismic presented and provided in two-dimensional representations. We may also be looking at the inside of the wellbore. Maybe it's an imaging tool like OBMI, in which case that's really a two-dimensional representation of the wellbore, the rock interface with the wellbore. We, of course, may also have three-dimensional sampling that we can interpret and work with, and that would be seismic volumes are a really great example. And once we've applied interpretation and built up a three-dimensional framework from the well logs, that becomes a three-dimensional representation of the subsurface. Now, an additional comment we could make around data types or measurement types is they have different types of measure. Like they could be categorical or continuous, and then there's different types of each. Categorical, well, this is the example where we don't have a continuum of representation of values, that there's discrete bins. It's discrete. That's categorical. A nominal case is in which we have distinct categories, but there's no natural ordering to them. Quartz, feldspar, limestone, wacky stone, bound stone. They're just different types of rocks. Built into them is no intrinsic ordering. Now, if we have categorical, but there's natural ordering built into it, that's ordinal. An ordinal is something where there are categories, discrete categories, but there's built into them a concept of order. Geologic age is a perfect example of that. Geologic age is really represented as categories: Paleozoic, Mesozoic, and so forth, Cenozoic, or we could talk about, at a finer scale. And we'd find out very quickly that, of course, there's natural ordering in time to them. Hardness scale, Mohs hardness scale for mineralogy, if you've been through those laboratories, I have, you'll find that they have like a Mohs hardness 1 through 10, and they have a natural ordering to them. Now, we can have continuous properties, in which case they exist over a continuum. They're not in discrete bins. And so with continuous, we have intervals. And an interval measure is one for which the intervals between the numbers are equal. And so this is something cooked into or built into any continuous variable that we'd expect, at the very least, that the intervals between the numbers are equal. In other words, the difference between 10 degrees centigrade and 20 degrees centigrade is the same as the difference between 30 degrees centigrade and 40 degrees centigrade. It's the same amount of change. But then we also have continuous ratio properties of interest. And these are interesting. These are ones in which the numerical property is truly indicative of the quantity being measured. So the Kelvin scale of temperature can be directly related to a concept of absolute zero and molecular motion, whereas centigrade temperature scale is artificially positioned. The values are just based on something that makes sense to us. It's all related to the phase changes of water. And so permeability, is one of those. Saturation is one of those. The numbers have actual physical meaning to us. All right. Now, if we're talking about types of data or types of measurements, we should also make a further clarification around the idea of quantitative and qualitative measures. And so quantitative measures are ones which can be written in numbers. We make the measurement, we can record it as a number. Qualitative information is about quantities that you can't directly measure. They require a layer of interpretation. So you could imagine that there are a variety of categories such as facies and rock types. There was interpretation that went into it. You didn't take a tool, walk up to the rock sample, and ding, it tells you, oh yeah, this is sandstone. No, there was an interpretation. There was a fraction of shale that you measured. There was maybe a grain size you measured. Maybe there were other types of cementation going on or something, and you decided that, no, this is a very coarse, porous, good reservoir sandstone. I'm going to call it that. So that's the difference between quantitative and qualitative. Now there's also, don't worry, there's only two more of these. Okay? There's hard data and soft data. And so what's the difference between hard data and soft data? Well, hard data is data that has a high degree of certainty. You make the measurement. Anything that's a direct measure will obviously be hard data. You measured it. It's got pretty good precision. Error is almost negligible on some of these measures. Example, and also if you have well logs, they tend to be pretty good. You have some uncertainties with regard to calibrations, different fluid types, or whatever assumptions went into the well log calculations to get back properties of interest, but the uncertainties can be pretty low. We typically treat that as hard data. We always have the option not to, though. Soft data provides indirect measures of the property of interest with significant degree of uncertainty. So then we represent this data as a probability density function for the property of interest informed by that measurement. And so in those cases, we don't get one answer, we get an entire distribution of possible outcomes at the sample location. That's soft data. Then we also have primary data and secondary data. This is super easy. It's very simple. Primary data is just the variable of interest at that step in the modeling process. If I'm making a model of porosity, porosity is my primary data. All the porosity data is primary data. Now, if I'm making a model of porosity, I'm using acoustic impedance correlated to it to help build that model. Now I'm in a situation in which I am working with secondary data. Primary data still remains to be porosity. Secondary data is the acoustic impedance. And so that's primary and secondary data. It could switch. I could build a model of porosity. Porosity was primary data by itself. Then I could build a model of permeability with porosity as secondary data. Permeability is now the primary data. So it will change with the step in the workflow. Let's talk about the distinct different types of data that we have with a little bit more details than I already provided. Core data, as I mentioned before, somewhat expensive. We don't get to collect cores everywhere we drill. It's because we have to trip out, we have to go back with the core barrel, it slows everything down. That's expensive data to calculate when it comes to interrupting drilling. What can we get from it? The core is beautiful. We can section it, we can see sedimentary structures. Core is basically the ground truth for establishing the paleo environment. What was going on? The depositional processes involved. It's essential. Now, of course, once again, I'm an engineer, but I've spent quite a bit of time looking at core, working with the geoscientists involved in a variety of different reservoir modeling projects and research. And so I can respect and understand the importance of core as far as ground truth. Excellent quantitative measurements of grain size, porosity. You get a lot of information about what's the depositional concepts, what's the depositional setting, the framework. and this can provide us great prediction information away from the well locations. We can use core in order to figure out facies, the facies that are present in the reservoir, and we will also use core to calibrate any well logs so that we can use our most accurate information for properties such as porosity to provide a ground truth for well logs, neutron density, and so forth that we're trying to use to infer the overall porosity along the well bore. Now a little bit more on core data. We have routine core analysis where we're going to, of course, calculate porosity, permeability, and saturation. We can, of course, as I mentioned before, we can use the core in order to get calibration for our variety of well logs such as gamma ray. We can also go ahead and look at core tomography and try to assess the overall pore structure, understand how the grains are put together. And we can do more detailed type of core analysis, special core analysis. We could look at the electrical measurements for SP. We can also look at calibration for NMR. We can do mercury injection and get distributions of pore throats to understand in more detail the overall permeability and the rock structure and its impact on flow in the subsurface. We can also try to understand relative permeability for multi-phase flow, which of course is more complicated. Well logs are of course much more common than cores. They'll be available in most of our vertical or subvertical wells, and so it's pretty common to have a suite of logs available to us. You'll commonly see resistivity and SP, and so from these are quite useful to be able to get a sense of the overall quality of the reservoir rock, but also to be able to see the overall bed boundaries, the fraction of shale. Gamma ray, once again, is also very useful for understanding how much organic rich shale is available in the rock, i.e. and how that might be correlated or impact porosity, permeability. NMR is all about, it's a board technology for medical imaging, and it responds to the presence of hydrogen, protons, and so you can quantify and understand the type of fluids that are available to you. You put the suite of well logs together, and you can use it to get a pretty accurate picture of what's going on with the fluid rock system in the subsurface. Now, of course, we also have image logs available to us in wellbore, and these are pretty incredible because you're able to actually see at centimeter or even sub-centimeter scale the micro-resistivity of the borehole walls. And so we can see effectively 360 degrees around ourselves in the wellbore, and we can see the changes at a very small scale. In fact, here there's reported a coverage at about 0.2 of an inch resolution, so really good resolution as far as seeing details. And we're able to see the changes within the rock around the wellbore. And so in this case, what you can see is that there's a lot of broken up clasts all mixed together, indicating a collapsed breccia. In this case right here, you can see that in fact what we have is dipping parallel bedding. So the parallel laminations that you often see within turbidites, maybe like a turbidite Boma sequence B, where you tend to have parallel laminations. And here we have a case where we have more chaotic type of structures, deformed structures, indicating some type of slumped or collapsed structure. So this might be like a debrite, not a turbidity current, but more of a collapsed structure in the deep water, or depending where it is. It might be some, I'm just guessing, but we can make a lot of interpretations from these image logs. They're very powerful. Of course, we have seismic information. So what we get back in the raw data is going to be the seismic reflections, and so over multiple angles and times. And this will be reported to us as amplitude data. And we can invert that data in order to get to acoustic impedance, which will tell us about the overall, rock quality. Specifically, impedance is going to be a function of the density of the rock and the velocity, acoustic velocity within the rock. We can go ahead and we can calibrate that with well-based seismic logs. to make sure that we have things anchored in the right location. And so this overall seismic is really important when it comes to providing a between well framework and away from well framework as far as the overall reservoir, the units within the reservoir, and at times the resolution is such that you can see individual the elements or the plumbing within the reservoir. Now, as I mentioned before, production data is really effectively our ground truth information. It's the one ground truth that we have. We're always curious, or we're always interested in the flow response of the subsurface. Well, production data is telling us how the subsurface is flowing. And so we can be interested in things such as bottom hole pressure, fluid, the production, the rates, the types, the temperatures. Of course, it's complicated because it's commonly the case that when we're looking at oil or gas or anything, water produced from a well, it's going to be commingled over multiple producing intervals. And this is hard to deconvolve unless we have some type of effort around logging the production rates cumulative over the well length, which you can do with a PLT, a production logging tool. At which point you'll understand that, oh, we seem to have a pretty good level of production here, but then we have some unit here that's producing significantly. Not much increase as we move up, so maybe this is not really producing, but here we suddenly have a jump. So this unit right here is contributing production, a little bit of contribution to production there, a big jump, and so forth. So these tools are quite useful to be able to see overall what the production is doing. So in summary, here's some ideas for data in the subsurface and the type, the resolution, the coverage, and what information you are gathering from the subsurface. What are the properties of interest that can be informed with this? And these are all the standard types that we talked about. I want to mention here, though, that there's a lot of other analog type information sources. In general, this is the idea of taking information from other locations and using them to try to understand our reservoir better, our region in the subsurface better. So we have mature fields. If you have a field that's very similar to the one that you're drilling right now and you're working on right now, but you've observed production over a long period of time, you've gathered a lot of data, information, so forth, that might be a powerful analog to help you with trying to figure out what's going on in the new field. Outcrop, that's very good, where you start going to rocks that are exposed at the surface that you deem are going to be the same as your reservoir rock or your seal rock or your source rock or whatever part of the reservoir system you want to understand. Geomorphology, you start looking at how landscapes and landforms change over time. And you start using that information to understand the process by which reservoirs are formed or reservoir seals are formed in the first place. Shallow seismic analogs. Shallower the seismic, the higher resolution. That's just how it is. You tend to get better resolution. You've got higher frequencies. They get filtered out first as you go deeper down, and so you can see more in the shallow seismic. If the rock has been the same for a long period of time, you can use that information as an analog for the reservoir. Experimental stratigraphy, Jurassic tank over there in the University of Minnesota with Professor Paola. Very cool stuff, right? And Kyle Straub, Tulane, and others are working on this, where you're putting mud, sand, crushed walnut shells, all kinds of different analogous materials into a tank with flowing water, articulating floors, and you're trying to mimic the processes involved in forming a reservoir or a part of the subsurface in general, in trying to use that to understand better. Numerical process modeling is, of course, becoming more popular now. This is where you build a reservoir in the computer, or the subsurface in the computer. You put the sediments in, you put the paleobathymetry or paleotopography in, you put all of the changes over time, and you can actually directly see the formation over geologic time of the reservoir. Extremely powerful, computationally very intense These are all possible information sources that can allow us to help us understand the subsurface better. So let's just talk a little bit about data preparation and cleaning, and then we'll be finished with this lecture right here. And so let's take this example of production in orange and flaring in blue from the Bakken, North Dakota. And so this is a really nice temporal data set to look at. And we could ask ourselves, okay, what questions could we ask from this data set? Production, right here, of gas being produced from the Bakken, and the amount being flared right here. Well, it's hard to look at. This data set is a little bit hard to look at. It's a little bit hard to figure out. So what are some of the creative things we can do with data preparation to help us? Wouldn't it be interesting to figure out what was the fraction of gas flared versus the production of gas per month? In other words, what is the ratio between the two? And so if we do that, what we see is this data set here now looks like this right here. This is the ratio. Simply the gas flared divided by the total gas produced. And so now we can start to see interesting patterns. What we have is some type of an early utilization where we had high rates of flaring. Infrastructure started to catch up perhaps. We have stable low level here of gas flaring. And then suddenly we have an increase in the proportion of flaring again, and it starts to level off again. It starts to fall. Probably infrastructure is catching up once again. And so by doing the simple calculation, we see something new in the data. This happens all the time. Now let's take this a step forward. Let's go back to looking at production and talk about what could we use this data set to do. Well, it'd probably be pretty useful to forecast the gas production in the Bakken going forward from the end of this data set. Rewind back to October 2017. Given this data, can we forecast what's going on forward? Well, do we have enough data to do that? What else would we need to know? Probably want to know something about drilling. How many rigs are in action at that moment? Maybe we have some type of knowledge about where we're drilling. We know something about the production profiles, current type curve analysis that's been determined for certain regions in which we are drilling. We want to know something about downtime for wells and reworking of wells elsewhere. We need to know a lot more information in order to make a forecast. We should remember this and be humbled by this as we're trying to make subsurface forecasts. We should remember that there's a lot of contextual information that has to be integrated. It would be quite naive to try to make a forecast just based on this data alone. It would be quite dangerous to imagine doing a linear extrapolation or something like that. We would need to understand all this other information available to us. Okay, so that's the end of my discussion about subsurface data. In the next discussion, I'll get into modeling goals and purpose. All right, stay tuned.